A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing. We continue in this lecture to discuss the Daubache or Daubachy's filter bank, which we had very briefly introduced in the previous lecture. I would like to put before you the salient points of that filter bank once again and then complete the design that I had begun in the previous lecture. So, recall that we had based the construction of this series of Daubache filter banks on the idea of annulling polynomials of higher and higher degree. So, we said that we wanted more and more factors of the form 1 minus z inverse appearing in the high pass filter. So, for example, let me put down the structure of the next member in the family after the Haar case, where instead of 1 you would have 2 factors. What we said was the second member of the Daubache family would look like this. The high pass filter would have a factor of 1 minus z inverse the whole squared. And therefore, if we look at the low pass filter, remember the high pass filter was essentially of the form z raised to the power minus d h 0 minus z inverse, where h 0 z is the corresponding low pass filter. Of course, I am talking about the analysis side. So, essentially the analysis low pass filter would now have a form like this. H 0 z would have the factor one plus z inverse squared. And then we recall that we had even lengths for the filters, and therefore, we have a situation H 0 z has 3 zeros, two already specified, obviously they belong to minus 1, and therefore, the third to be determined. And where do we determine this third root from? Well, we go back to the requirement of orthogonality to even shifts. So, recall that we had said that the impulse response is orthogonal to even shifts. That means, if I assume that this filter has the impulse response h 0, h 1, h 2, h 3 at 0, then this is orthogonal to its shifts by 2, 4 and so on. So, the non-trivial case the only non-trivial equation that we get is the following. It comes from a shift by 2. H 0, H 1, H 2, H 3, and when this is shifted by 2, you have H 0, H 1, and then they are all zeros after this. There are zeros before and there are zeros before. So, all that you have is H 0, H 2 plus H 1, H 3 is equal to 0. This is the only non-trivial equation that we get. Now, from the location of the zeros and the free parameter, we need to express H 0 through H 3 in terms of the free parameter. So, what do we have? We have H 0 plus H 1 z raised to the minus 1 plus H 2 z raised to the minus 2 plus H 3 z raised to the minus 3 is of the form some constant, let us say C or C 0 if you please, times 1 plus z inverse the whole squared times 1 plus B 0 z inverse. And we need to compare coefficients on both sides. Now, the constant C 0 does not affect orthogonality. So, we shall just focus on the rest of the expression, because we first need to satisfy the requirement of orthogonality to even shifts I mean, and from there we need to determine the constant C 0. We will see later what helps us determine C 0. So, in fact, if you look at it, what we are asking for is the following expanded term 1 plus z inverse the whole square times 1 plus B 0 z inverse, where B 0 needs to be determined. And this, as we said, could be expanded as 1 plus 2 z inverse plus z raised to the minus 2 times 1 plus B 0 z inverse. And if we collect terms, it gives us 1 plus 2 z inverse plus z raised to the minus 2 plus B 0 z inverse plus 2 B 0 z raised to the minus 2 plus z raised to the power minus 3 times B 0. So, we will aggregate terms together here, we will take the coefficients. So, essentially except for the constant H 0 is essentially therefore 1, H 1 is of the form 2 plus B 0, H 2 is of the form 1 plus 2 B 0, and H 3 is of the form B 0. And now, we can write down the orthogonality equation that we seek. It says H 0 H 2 plus H 1 H 3 must be 0, implying that 1 plus 2 B 0 plus 2 plus B 0 into B 0 is 0, where we are effectively saying 1 plus 4 B 0 plus B 0 squared is 0. So, there we have an expression for B 0. It is easy to determine. So, B 0 has got constraint, as you see, not surprising. There was one free parameter and one non-trivial constraint. Solving the equation, we have B 0 is minus b plus minus root b squared minus 4 a c by 2 a. That gives us minus 4 plus minus 2 root 3 divided by 2, and that gives us two solutions, minus 2 plus minus square root of 3. Now, we have two solutions here. Which of them should we choose? Well, what distinguishes these two solutions? It is very clear from the quadratic equation, and let me go back to it. You see, if you look at this term, this tells us the product of the roots, the term 1, and the product of the roots clearly has a magnitude of 1. So, if one of them lies inside the unit circle, the other must be outside. In fact, they cannot lie on the unit circle, because none of them has a magnitude of 1, and therefore, one must lie inside the unit circle and the other outside. Let us take note of that. In fact, it is very easy to see which lies inside and which lies outside. If you look at the minus 2 minus square root of 3 solution, it clearly has a magnitude greater than 1, and the other one has a magnitude less than 1. So, among the solutions, B 0 is square root 3 minus 2 lies inside the unit circle. And B 0 is minus square root 3 minus 2 lies outside the unit circle. Now, we have a choice. We could either choose this or this. We shall choose this, and there is a reason for it. You see, very often we like to choose what is called the minimum phase solution. There is this idea of minimum phase. I shan't dwell too much on it at this moment. Suffice it to say that minimum phase essentially means choosing all zeros inside the unit circle wherever possible. In fact, the idea of minimum phase comes from what is called minimum phase delay. So, when we after all, one interesting thing is that whether we choose the root inside the unit circle or outside, the magnitude of the frequency response would be the same. The magnitude would not be different. What would be different is the phase, and when we put the root outside the unit circle, there is going to be an increased phase delay, and very often that would also point to an increased group delay. Increased phase delay, increased group delay in the filter. So, when we take the solution inside the unit circle, we are reducing the phase or the group delay as much as we can in the filter. So, it is essentially a question of choosing the better solution in terms of phase. So, let us summarize that. We take the minimum phase solution. That is B 0 inside the unit circle. And we have B 0 is square root 3 minus 2. Obviously, mod B 0 is less than 1 here. And one can also evaluate this approximately. If you recall, square root of 3 is about 1.73. So, this would be 1.73 minus 2, and one can come up with an approximate value. That is not really an issue. Anyway, we can now put down the impulse response of the Dobach low pass filter therefore. It is essentially Well, let me read off the impulse response from here. Let me flash the impulse response before you once again, and then we will substitute. So, this was the impulse response. Now, we substitute for B 0. So, 1, 2 plus B 0, which is essentially square root 3, and then you have 1 plus twice B 0, which is 1 minus 4 plus 2 root 3, or minus 3 plus 2 square root 3, and finally, B 0, which is just square root 3 minus 2. So, this is H 0 of course. Well, please remember this is to within a constant. So, there is still that constant C 0 that needs to be determined. How do we determine the constant C 0? Well, we go back to the original equation of kappa 0 z that we had. So, we wanted kappa 0 z defined by H 0 z times H 0 z inverse to obey the following. Kappa 0 z plus kappa 0 minus z is a constant. And in fact, what it really means is we now need to choose this constant. Choice of C 0 means choosing this constant. The easy thing to do is to ensure that the impulse response has a unit norm in the sense of L 2. Because if you look at it, the dot product of the impulse response with itself, what we are saying essentially is kappa 0 z, the sequence corresponding to kappa 0 z at the 0th location is essentially the norm in L 2 z, the norm squared actually in L 2 z of the impulse response. It is the dot product of the impulse response with itself, and we could as well make that 1 for convenience. So, now we shall choose C 0 in order that this becomes 1, and in fact, I do not need to carry out the computations. Essentially what I am saying is choose C 0, so that C 0 squared times H 0 squared plus H 1 squared plus H 2 squared plus H 3 squared is equal to 1 with H 0 through H 3 as chosen before, without C 0. So, I leave that little calculation for you to do, and I would strongly recommend that students look at various texts that list the Doobash filter responses and verify that the Doobash filter response for a filter length of 4 exactly coincides with what we calculate from here. So much so for the Doobash filter bank. Now, the next step is to build a phi t and a psi t. How would we do that?